some of the computers are working now, so before you go forward. So the idea is to do what we were talking about yesterday, about making a synthetic spectra from galaxies and understand how the spectral shape and features change when you change the properties of the galaxies. Okay, so if you have galaxies with different star formation rates, metallicities and dust, etc., the shape of the galaxy spectrum will change, and we are going to look today how it changes with different properties, because this is how SSPs, the simple stellar populations, are built on. So the first thing you will do is to get a little bit familiar with the words that have been used in this software. So you can do that by first going to this FSPS link, and under that it explains to you how to make a galaxy basically. So if you go into modeling stellar populations part, it tells you how to make a simple stellar population by giving certain parameters. So first you import FSPS, then you do FSPS.stellar population, which means you're now generating a stellar population, and afterwards you're giving parameters of your stellar population. For this, there are some things that are already defined by default, which you need to understand what they are, and that are some of the questions, and some things you can specify. For example, if you want the metallicity to be solar metallicity, you say log z is all equals 0, for example, and you can define these things, okay? And then you do, then this creates a thing which you can look into later. So the first thing is perhaps afterwards to go through the list of things and understand what each of these means, and that is in the FSPS manual folder, and you can look at to that in the PDF under sections 2.1, 2.21, 2.12 and 2.2.3. All right, and then you will make the default galaxy spectrum. After you go through these default answers, like the things that are already defined by default in the FSPS, which you can change as well. And then you can make a galaxy with a single starburst for different years, but make it on the same figure so you can see how the spectrum changes with time when they evolve. So if you are looking at a galaxy which is actively forming stars, you would see something like these two. But if you are looking for a galaxy which is around our neighborhood, around our Milky Way, which is older, you will see something like this. So if you make it on the same figure, you can see how the spectrum changes with time when there is only one single starburst without any star formation after that. Then you will change that into a constant star formation history. That means the galaxy is now forming stars in the same rate for all the million years. And then you can change the parameters to be no dust with no nebula emission, and then check how the spectra changes when the galaxies are forming stars continuously. Then you will add nebula emission, which is the one that I was talking to you about yesterday, when the stars are heating up the dust regions around the neutral gas around the star regions. It gives rise to strong emission lines, and this is what you see as hydrogen H alpha, oxygen lines and nitrogen lines, etc. So we can turn it on and you can see how the spectrum changes, and this will look like a real galaxy at this point. Then you can change the metallicity of the galaxies and see how this changes, and all of these figures. So this you will make again in another figure with the different metallicities, so you can see how the different metallicities vary the features of the galaxies as well. Then you will do for dust as well, and when you do dust, increase the wavelength coverage to 100,000 angstroms to go beyond, and for that you might have to log the X scale to make the spectra smaller, because for dust it is important for us to see how the re-emission of dust works, because when the dust gets hot, it will start to re-emit in the longer wavelengths, and this is what you will be checking as well. Then you will change the dust extinction parameters by these values to see when there is a lot of dust, how does the spectra look like compared to galaxies with less dust. Then you will complicate the thing by looking into a more like a real galaxy, evolution in the universe by changing the metallicity with time with different redshifts to see what you would look like a galaxy when it's in the early universe compared to what we see today. And if we manage to get it done by the afternoon, in the evening today, for tomorrow, like depending on the time we have in the afternoon, we can then use that to see how we can make real observations of galaxies match with the models. Do you get what I mean? Because these are still models, right? So then if you have a whole grid of models done, then you can compare with the observations to see what is the metallicity of the galaxy, what is the star formation rate, etc. This is what I was planning to do today and tomorrow. So, but because we couldn't do the class yesterday, we'll try to get it done today. And tomorrow we can go into matching the observations with data. All right? So start going from the top. Ask me any questions, any problems. So only thing you need to do is first, it will be easy if you make a function to make figures, because you can easily use the same function to make the figure over and over again, because you are just changing a small parameter and replotting the plot. So it might be easy if you just make a one function called make figure or something like that, and do it that way. Okay? Any questions? Thing that you did not understand? No? Okay, good. Okay, so please go ahead if you. Because we only have like 15 minutes left, let's go through some of the answers maybe. I managed to do up to 9, and so I'll upload these answers as well to the website. I won't do 10, I'll let you do 10 yourself when you get some time to do things. All right, yeah? So how far have you done? Some groups have done up to 6 or 7, I think. Anyone has done more than that? 8, okay, yeah, good. Okay, 9, no, okay. 9? Oh, okay, yeah. So good you didn't do 10, because there's a spelling mistake in 10. So like I've corrected these things in the thing. So when you're using at home or something like that, use the newest version I will put on GitHub, not the ones that you're using. I've made some changes to the explanations of the questions just to make it more clear, you know. So all right. So the first thing is you might need Matplotlib and NumPy, I think, to do these things. These things you can look from the manual. Z continuous means how it interpolates the metallicity from the SSP to the CSP. Star formation history is 0 means it's SSP, so it forms stars at t equals 0 and then evolves that population, and there's no new stars getting formed. Yeah. Log Z sol is just the fraction of the log metallicity between the solar compared to the solar metallicity. So the easiest way I was showing people to do the log Z factor in your code is, if you have log Z sol, right, is to use numpy.log 10 like this. Use the function like this to say what it is. So you can put here, for example, if you're using 0.1 or something like that for the calculations, you can do like this, because it's always given as a fraction of the log of the fraction of log of solar metallicity. Okay, so that might be easy way, so you don't have to confuse yourself between the answers. So dust type means what is the dust attenuation you're using. So number 2 means is Calzadi dust law. So this is for the star forming galaxies around our Milky Way, starburst galaxies, as you would say. So that is kind of appropriate to use for star forming galaxies, but there is also other dust laws that you can play around with. If you use dust type of 2, the manual says that you have to specify explicitly that dust 1 is 0. So when you do these things, always the dust 1 parameter should be kept to 0 if you are using Calzadi dust law. And dust 2 means the other dust factor, which is the optical depth of the gas clouds. The optical depth is kind of related to the extinction. In Calzadi dust law is about 1.08 times, so it's almost the same. So you can use it interchangeably. That's fine. All right. Any questions of these ones? No. Okay, so IMF, you have to check what IMF that is getting used. I think it's the default. Did anyone check that? I forgot to look into this. Group IMF. Okay, so group IMF is done for globular clusters around our Milky Way. So it's kind of one of the parameterizations. It doesn't really change too much, as I mentioned, but you can of course use your own law and then change the values as you need. Stellar libraries and isochrones, I think is Mills and Basti, right? Basel or something, right? Yeah. And you can change that in the, you have to change it in the FSPS, not in the Python package. And how to change it is given in the manual as well. The gas phase metallicity is normally kept to be the same as the solar metallicity. But you can also explicitly change this, because I was explaining to some groups in the morning that if you have a lot of stars contributing, they have a lot of supernova and stuff, and all the gas around it will get enriched from the metals coming out from these things. So what happens is normally the star metallicity will be lower compared to the gas phase metallicity of these systems. So it is normally kept to be the same, but a lot of people are nowadays using two different functions to define the two, and you can put it as a function in this program as well. Intergalactic medium, there is an equation I think which is defined there. Can someone say what the name of that thing is? How is the IAGM handled? What is the answer for this one? How is the intergalactic absorption handled? Okay, so Madhav, okay, so he's if you look into the paper, he explains how the absorption works out. It's just an analytical equation. So it just takes the spectrum, and basically anything below 912 angstroms in the spectrum will get absorbed. So like if you see anything, it will be always be anything below that will get absorbed and get from the spectrum, from the IGM. Is dust emission included? Technically it is included in the models unless you remove dust by removing the gas mass dust extinction, or from you can explicitly state that as well. Nebula continuum is not included by default, I think, but you can include it. We probably did later on as well. And nebula emission is nebula continuum is normally added, but nebula emission is not included by default. And the difference is that okay, we'll come back to that later on. Alright, so the next thing was to just make some plots for a single starburst population using these colors. So as I told you, it might be just easier to write a function quickly to do all the things at once, so rather than changing things later on. And I think a lot of people did this. It should look like something like this. So you can see at the very beginning of the starburst, everything looks blue and there is not much features. And with time, you can see these absorption lines being more prominent at later times. It is because these features come from the older stars, so they have to be produced. They have lifetimes of few billion years. So after a certain time, you can see these absorption lines coming in, and you can see there is not much evolution between the last 3 billion years, because there is nothing much happening in the stellar population. It's just the older stars are getting much older because there is no new stars getting formed. Anyone has any questions on this? No? Okay. And you can compare with your neighbors. Well, you have about 5 neighbors each in a group, so I don't know. Okay, anyway, yeah. So what is the kind of the difference you think between this population and a normal galaxy? So the model that you made to 3 compared to a real galaxy, what would be different?
So basically, is that the galaxy, in the model that is SP, when the galaxy is doing the star course, the SP says that the stars begin to form and then die and doesn't form anymore. So this is what we don't see that in the real galaxy.
Yeah, so that's almost exactly the answer. So because in a normal galaxy you'll be forming stars in different ways, so you have to consider this, and that is why we discussed yesterday that you go from a simple star population to a composite stellar population by combining these SSPs in different ways, and that is what we are doing next afterwards. And also, like in a real galaxy, there is galaxy interactions and other things which are not considered as a whole anyway, so there are more complications. And then we started making a constant star formation history model, right? And with certain parameters as here, like with no dust. And you can see like whether you got, I think you all also got this similarly. And you can see that the what is called when the galaxy gets younger, the spectrum changes with time. And then but the blue part of the spectrum is now stronger compared to the earlier values, right? Because the older ones are also forming stars, so there is always UV flux coming for these galaxies. So there's not a very big difference, but you can also see the absorption lines getting prominent. And then you can add nebula emission lines and the nebula continuum, and you can see that now the lines pop up from the spectrum. So earlier there were no lines. Yeah. And there is two things. There is a continuum coming from the H2 regions as well. So you can, if you want, remove the emission lines, but keep the nebula continuum and then see what the differences are, because these are two different parameters. Emission means the lines. Continuum means the continuum coming from the nebula H2 regions. And if you only add the continuum, it will just increase the flatness by a tiny little bit. And but you need to put emission to actually see this emission coming out as well. So when you look at a galaxy spectrum, you normally look into these regions to identify different elements from this, and from that you can link into properties of galaxies to see what is the star formation rate, metallicity, and other parameters. All right. So the next thing you did was to change the metallicity of the same model to 1/10 solar and to solar metallicity. And if you zoom into these plots, two different plots, you might be able to notice differences in the emission line strength, and also in the normalization a little bit. Because what happens is when you have low metallicity galaxy systems, you have very hard ionizing what do you call the hardness of the ionizing field goes up. So this means that the emission lines can become prominent, but also like some of the emission lines will be lower, because when you decrease the metallicity, the abundance of elements goes down. So this is not like one-to-one relation, but there are certain lines that you can look into the ratios between lines to infer the strength of the ionizing radiation, and then compare that with the metallicity. So for example, in the normal observations, the oxygen 3 to H beta ratio, for example, and like N2 to H alpha ratios will give you like the regions of star formation compared to AGN activity and stuff, which you can use to understand how the strength of this ionizing field is. Then you can use the oxygen abundance, and which is normally computed by you can also calibrate it with N2 to H alpha ratio to compute the metallicities of these systems. And normally the metallicity has a lot of different definitions, but the most commonly used is the oxygen abundance of these galaxies, which you can measure by looking at the O3 oxygen emission line as well. Okay. So normally when people call metallicity, they will give you in a scale of 12 plus log OH is what is commonly used. If you look into papers, you will have something like this. So it's oxygen abundance plus log 12. So this is kind of from the solar things. I think solar is about 8 point something. And then you can see galaxy, and going lower from 8 means that the metallicity is lower, and going up means metallicity is high compared to the solar metallicity. All right, and you can like zoom into these regions and look at the differences. You can plot the two metallicities in the same plot as well to get more ideas. Last one that I did is adding dust to the models. Now you have different extinction times, and at 20 million years I've increased the plot region a little bit. Now you can see the difference in the spectrum, because if you have no dust, which is shown by the blue, the spectrum is very flat. This is what you were seeing all this time. But when you keep on adding dust, you can see the UV part of the spectrum getting more, and optical part a little bit getting more and more attenuated, because when the wavelength is shorter, the optical depth is higher, so this part of the spectrum gets absorbed more compared to the near infrared parts. And that is why this region of the spectrum is more immune to dust properties. So that's why you would observe this part to get the estimates of of mass of a galaxy, and you need this part to be corrected to get the estimate of star formation rate. And the other thing you will notice is that when there is no dust, the dust emission is not there almost. You can see the pH lines, but not the dust emission lines. This is because there is no dust getting re-radiated. But when you add dust into the models, then the dust will get heated up from the star formation, as you would see, and then the emission from the dust will increase. And you will see there is massive features coming up here, like which are very broad. They are called the polyaromatic hydrocarbons, PAH lines. And these are like all the lines that are made in dust basically, because the dust consists of these hydrocarbons, and they start emitting energy that is getting absorbed from these UV photons, and you can see these prominent emission lines in this part of the spectrum. So you can increase the wavelength range, and it goes beyond. You can see how this strength changes, and this will also be will depend on the dust gas mass and other properties. So I made a small note here that you can look into dust mass, and there is also like Drain and Lee model parameters if you look at the PDF file, which will determine also some parameters that will give you the strength of these emission lines. So it's basically when you want to measure the star formation rate in normal galaxies, that is why people use something called the UV plus IR star formation rate. So you compute the total UV flux and the total IR flux using SED fitting or other methods, and then you kind of get the star formation rate independent of dust attenuation, because here if you only have the UV, it's really hard to understand how much dust attenuation is here, right? Because there is other star formation rate will also bring this thing down, as we saw earlier. So this change is also similar to the change that you saw earlier when you have like for example a starburst population or something, right? Because this will also bring it down. So you don't really know, like it's hard to disentangle. So that is why you would combine the two star formation histories together, like the UV part and the IR part together, to get the total dust emitted energy that will give you an indication of the star formation rate in 100 million years time scales. The next thing to do, this is one of the things I changed. I forgot to put the time that you need to compute the spectra, so I've added this now. And you're combining all the things to be in different redshifts. At high redshift, the metallicity is very low. At 100 million years, then you can increase the redshift, and the little bit of dust is now there in the systems because the galaxies are older. With the same metallicity, then you increase the dust to come to lower redshift, and then at 13 billion years at redshift 0. And then you can do the same thing, but it looks like the code does not redshift this properly. So when you do the redshift, there is don't forget that you have to increase the wavelength if you want to get the redshift effect correctly. And also you need to consider the luminosity distance, because luminosity will get reduced by the distance, right, by a 1 plus z factor. So because the galaxy at redshift 10 will be fainter compared to the galaxy at redshift 2 if all the other parameters are the same. So once you compute the wave and the flux, make sure that you redshift the spectrum if you want to check that, and then decrease the flux depending on this factor, if you want to look at how the actual real galaxy would look like. All right. And these are the 10 things we wanted to have a look today. And is there any questions on these ones? So the manual is really cool. So you can it is very comprehensive. So you can look at the PDF manual and also the Python version of it. And that will give you a lot of information if you want to play around with this. So there's a lot of knobs, as you see, that you can change. If you look at the manual, you see there's a massive, right? A whole 3 pages of things you can change. So that is a problem, because if you want to fit the data to models, there is so many things you can change, so we don't really know what is the best way to connect these things. So in tomorrow, We managed to get it installed, I think, and they're copying it now. We can use one of the softwares called FAST, which actually uses similar models like already pre-computed models, and then it will fit to observe data to see to infer real properties about real galaxies. And we will try to do it tomorrow afternoon, maybe if we have some time in the morning as well to do the software. And I think this room is booked for the morning, so I will also tell Esteban to email everyone. Perhaps we can meet here. So I will give you a quick introduction to fitting CDs to get the real information out from galaxies, and then we can play around with the software a little bit, so there's more time to do it before we finish off. All right, so today was just to get an idea of making these synthetic populations, and tomorrow we will fit real data together to get what the universe is telling us. All right, cool. See you tomorrow then. If you have any questions, you can just email me or whatever. And like I will keep this updated as well. So anytime you want to update this thing, just go to the same folder and just do git clone and this link. So it will automatically rewrite the files that have been changed. So you don't have to waste internet to re-download every time. All right? Yeah.